Hi, my name is Vahan Davoudian. I'm a physics experimentalist for 30 years, and I have always replicated so many experiments with the scientists as much as I could if I had the material, if it wasn't like astronomy, so it was beyond my reach. But overall, it did not mean that I did not trust them, but I just wanted to make sure that I can do the experiment. My inspiration came from sports, natural, insects, and animals. And overall, I had so many speeches in CU Boulder and then DeVry University and Regis College, and the student loved it because I started with basic. It wasn't complicated a lot. I did not use any formulas, and they loved it. So far, I have published 49 theories, and this is going to be the 50th. I have 20 or 25 more, so hopefully I will publish every 21 or 1 month from now on. And so many people emailed me. I'd like to thank, that is so rewarding for me, because that is the way you guys are encouraging me to upload more videos, and that was so amazing. I just wanted to appreciate that, and I could feel it. Most of them were young generation, because they have a good passion for science. And then the reason why they loved it, because I have to clarify this, my experiments are unique. I have never seen in any physics books or any lecture in universities or any colleges or any physics books or anything like that. Even on videos, they're entirely different. Like this one we are doing is called How to Visualize Michael Faraday's Lines of Forces. And I will explain exactly. I have 22 experiments you have never seen in your life, and they are all based on science, and they're entirely different concept. Because most of the time, what they do, let me show you. I have seen so many YouTube videos, and this is the way they do. They put, like ferromagnetic here, and they get something like this, and then they go back and forth and back and forth. And this is the old-fashioned way. And in fact, this is the way Michael Faraday did. And he was a great scientist, and his precision was beyond my imagination. How he did it, I don't understand. Let me post this. You can see how good he was. Oh, by the way, forgot this. So, How to Visualize Michael Faraday's Lines of Forces by Vahan Davoudian, physics experimentalist. And this is my email, vahandavoudian@aol.com. Lines of forces, practically, they diverge in space, but when they get to the pole, they converge. Now I have to show you in a minute. And this is the one Michael Faraday did in 1820s. Let me post this, you can see. It's just so easy to understand. What he did, it was amazing. I mean, it was breakthrough in science. No one had ever done this before. See, this is a bar magnet. You can see the precision. Michael Faraday was an amazing person. I mean, if you go to a dictionary or anything, you type in experimentalist, Michael Faraday comes. And then he was one of the greatest. Well, of course, there was another one. His name was Henry Cavendish, and he was amazing. By 70 years old, he was doing the best experiment ever. But Michael Faraday did not continue after like 60 years anyway. So this is a bar magnet, and then you can tell the lines are exactly, parallel. Well, of course, you cannot say 100%, but amazingly, I found a book in Los Angeles. It was published 1960s, I believe. At that time, I remember I had to pay $100 because that book was so rare. You could not get that book anyway. And then when I studied, I realized it is not mentioned in any physics books whatsoever. All these lines, they repel each other. Can you believe? And they have the speed of light, and then I will explain later what happened. And imagine, Michael Faraday did, and most of his experiment, because I have a good book from him, it's like 2,000 pages. And guess what? Most of the time, he would love to use this round magnet or cylindrical. The reason why, he was so smart. Ordinary magnets like this, bar magnet or, things like that, they are not symmetrical like this. But the good thing about this magnet is, it's all around 360 degrees, they're the same. But you can see the lines, it's 360 degrees. And this one is repulsion, and this was is attraction. But I will explain with my experiment. Like I said, they're unique, and I'm hoping by end of this video you guys will learn a lot. And then I would appreciate if you pay attention, because they're all science. It is not guessing or anything. Everything is based on science. This was my analogy for why the lines of forces repel each other. Of course, I have like 6 posters, and then I will start the experiment, and then you can see how comprehensive, how good they are. Most of the time you can see the kids are playing, and this is plastic, and no matter what, you get static electricity, and you can see this girl is sticking up because it's natural. I mean, they all have negative charges, but this young girl is different. The reason why she's touching the generator, and it doesn't matter, and the buildup in her body is all negative. That's why her hair is sticking up. This is exactly what happened with the flux line. By the way, flux means in Latin means to flow, but Michael Faraday, he would rather use the lines of forces, which is exactly the same. I mean, it doesn't make any difference anyway. Let me take those off. I have 2 more. In fact, I compared lines of forces to Niagara Falls, but I'll tell you why. I was here 34 years ago, and my kids were so little, and they were so excited to see this natural phenomenon. This is the only one in the world that, it's just beyond my comprehension, beyond my imagination, how good it was. And then we spent here like a week, and then we were going almost every day. There was so much excitement, and this is amazing. So I compared this with exactly with flux of lines. Why? Because it is flowing continuously. We have no idea how many million years they're flowing. But it's exactly like flux lines. And I will explain in a minute. And the magnet, it doesn't matter, round, square, or any donut shape. The lines are going 360 degrees continuously, and like I said, the speed of light. So imagine when you have the water flowing like this, it's exactly like a flux lines. And this is almost 51 meter high, and 168,000 cubic meters is coming down every minute. And imagine how much kinetic energy is involved here. It's unbelievable. You may not believe this can create not billions, trillions of joules, which is amazing because it's always flowing. All we need in electricity or induction, according to Michael Faraday, all you need is a magnet and coil, and all you need a relative motion. It doesn't matter. Coil moves or the magnet moves, you get the induction. And of course, they get millions of volts from here, and any fault, not this fault, that is a good analogy that, they always flowing. This one is about the James Clerk Maxwell. Let me put this on. I'm thinking after, like Sir Isaac Newton, James Clerk Maxwell is one of the icons. one of the greatest scientists ever born in the history of mankind. In fact, you know, he was, I think, older. No, Michael Faraday was a little bit older than him, but they had correspondence. At that time, there was no phone or email or anything, but they loved each other because, you know, James Clerk Maxwell was an amazing person. He loved technology, he loved science, and he was the only one. He became the professor in Oxford, which is one of the most prestigious university in history. So he wrote a letter to Michael Faraday, and he said, Michael, I'm getting my bachelor, and I was wondering if I can use your lines of forces for my thesis or for my dissertation. Michael Faraday said, yeah, with all due respect, go ahead, because I know you are the scientist. And you know what? Michael Faraday had a good heart. Unfortunately, he didn't have education, but he was one of the best experimentalists at the time. And Michael Faraday did not realize after a few years, and then even after his death, that you know, James Clerk Maxwell is an amazing scientist. He would formulate everything, because in science, if there is no formulation, science doesn't mean anything. Well, of course, I'm not using today, but James Clerk Maxwell formulated everything, and it just happened to be, you know, there was a poll, and then they realized his equations are much more effective than Albert Einstein EMC square. So he wrote a letter and said, yeah, I'm going to use this, and you can see this is a magnet, and then you can see, well, of course, it doesn't show everything. They start from north to south, and then it continues 360 degrees. I will show you. My good idea was that, you know, I used a slinky, I will show you in a minute, and this continues all the way. So all you have to do, you cut through these lines so you can get voltage. In other words, if we have no electricity, if we don't have flow of electrons, we cannot live. See what James Clerk Maxwell did. Albert Einstein was not even born at that time. And imagine, he said single electric field here is disturbed by this, you know, uniform lines of forces. Well, he meant exactly the same thing happened on Earth, and then he wrote a letter to Michael Faraday that, Michael, what you have like a line of forces in on magnets is in space. And you know, he learned a lot. And the poor guy, his vision was not as good as Maxwell, because Maxwell had higher education anyway. But see what happened. Albert Einstein probably got the idea from here. The only difference is he used, instead of this electric charge, he used mass or planets. So he said they put dent. So you can see here, this electric charge is putting dent on the fabric of this universe, or fabric of this. But you know, of course, one day we will talk about James Clerk Maxwell, because he was amazing scientist anyway. I have great respect for him, but the poor man died when he was only 48 years old. And what a pity, such a great scientist died so young. I mean, 48 is nothing. Okay. This is another one. You know, most of the time when I sleep or before I go to sleep, I watch the Science Channel, especially NASA and so, and all of a sudden this crossed in my mind. I said, wow, this is the only way you can promote the science. You have to compare something. We say Los Angeles, New York. You say this is as big as planet Earth. This is smaller than moon. This is smaller. And then I realized I can compare the, you know, lines of forces exactly to light rays. And when I was in college, I remember this was my favorite subject, lenses. Well, of course, I just wanted to become, you know, optometrist, and then I changed my mind anyway. And imagine this is a convex lens, and it doesn't matter how many light comes in. Light rays, we're talking about trillions of trillions, but they focus over here. You see, it's called focal length, and then I consider this like a north or south pole. If you have another one back to back here, we can focus another one here, so it'll be exactly like north and south. Now I want you to pay attention now. I'm going to start this experiment. But before I do that, I just wanted to show you something. Most of the time you can see all these scientists, what they do, they have magnet, it doesn't matter what magnet, and then they slide it back and forth, they slide it back and forth like this. So what happened, they are showing how this, ferromagnetic or, highly, or, and then I realized, one, you can go one step further. So what I did not slide it back and forth. I just rotated. You see what's happening? When it gets to the pole, they're sticking up. When it gets to this side, which is not the pole, they're flat. Did you see what happened? Yeah, I hope you can see this. Let me bring it a little bit closer. See? Now it's sticking up because it's no North Pole. See, when you go 360 degrees, now it's not the pole. You see how flat they are? And then I had to prove this scientifically, but there's one exception only. I love this. This is called horseshoe. This is the only one is showing that, two poles are, facing each other. And this horseshoe magnet has so many applications in science anyway. We put this back over here. I had to make my own magnet and the earth flux, lines of forces and so on. So, see, imagine there's a bar magnet inside here. See, this is a bar magnet, and I made my own magnet. So you see these red lines, these are exactly like a flux lines. Why? Because they travel from the north to south, and then it's continuous. Well, of course, this is exaggeration. They're not that far apart. And imagine this part is called space. Why? Because see how far apart they are? So they are diverging in space and converging on poles. And it's always from north to south, and it's always continuous. And this is just a hypothetical, guess, or, if I compact the earth, it's going to be like this. It's going to be like magnet. Exactly like a magnet. So no matter what, we have north and south here, but the earth has, north and south, and then has a magnetosphere. It doesn't matter. This is the best way I could find, and it's just easier to understand than visualize. What do I mean by lines of forces? I think, yeah, I thought about this for almost a month, and finally I got the answer. And imagine, now you can see the North Pole over here. You can see the North Pole right there. And then these are all flux lines. And you can see, imagine, it doesn't matter by the poles, by the sides, where the poles are not even there, it's continuous. So if I cut this and then like a cross section, it's going to be exactly the way I showed you a few minutes ago. And this it's continuous. Regardless of what shape that magnet is, it's always continuous. And this one is a bar magnet. Let me show you. It is using the same principle. So normally these bar magnets start from 1000 Gauss and over. If I cut this, it's going to be exactly like Michael Faraday's lines of forces. Well, of course, what he did, he showed here like half of these lines, and you could see they are going to the sides, and then they spread, and then exactly equally. It doesn't matter, but always when you want induction, you get more induction by the poles because there are more charges, and then I have to explain what happened. These charges are traveling, and then they end up in the center of the magnet. You may not believe I went through the hell, because it took me 1 week to have a hole in a magnet. I had to spend a lot of money in Home Depot and so, have the best, bits. Finally I made a hole in a magnet. I realized inside the magnet, the forces are unbelievable. It's exactly like you can't go inside the earth. If you go inside the earth, the magnetic field will kill you. That is how bad it is. So this is another one, and like I said, if you cut it in half, you can see exactly Michael Faraday's lines of forces. But I had to use a fantastic device, and I remember I showed this in so many experiments. I bought this 30 years ago, and let me turn this on. Now the same thing is $1,000. At that time, I remember I bought like $400. And you know what? I don't want to guess. Always when I do everything is based on science. And this gas meter is called DC gas meter. I hope you can see it over here. Let me show you one. See, this is a cylindrical, and then each pole has 1,500 or 1,600 gas. Let me see how I can show you. See, this one is 100, oh, 1,800. How about that? Let me see, this pole has 1,650. So I realized if I don't have this gas meter, I won't be able to prove my theories. And this is the only way I could prove my theories. And how could I do that? With this. So I realized this is the only way I could prove this. So another thing, I was so happy with this. And now I start the experiment. I said, how could I get the flux lines? Because, you know, when we're talking about Michael Faraday's flux line, you have to know the science, you have to know the geometry, because these are all in space. You may wonder why they're sticking up like this. See, why? A few minutes ago I explained, they repel each other. It doesn't matter, they're all on the north or south, but see what happened? See? They repel each other. But you know, we don't see on a magnet because they're invisible. But this is the only way I could prove it to the science lover. This experiment had never been done before. And this is so unique, and I want you to pay attention. So what happened? See, they repel each other. But the exciting thing here is, see, this is mounted on a north. If I bring the north here, they are going to spread. Let me see if I can show you. Did you see they spread? They don't bunch up. But on the other hand, if I bring the north, you can see they bunch up. See? And finally, they attach. But what if I have two like this? See, imagine, most of the time we say we have two magnets, and even in your high school you can learn north and north, north and north, or south and south, they repel each other, and two different ones, they attract each other. But you know, you have to have explanation. Why? What happens scientifically? So this experiment substantiates my idea, and then it shows to the student or whoever is the physics lover. So now both of them are on N. No. I'm sorry, this one is not. Oh yeah, this one is N. I hope this one is also N. Let me double check. No, this one is S. So I'll show you something. See, this experiment is so unique, and you would love to watch them. So you see, imagine I'm holding two magnets, and both of them are facing, they are the same polarity. So north and north, or south and south. See what happened? Did you see what happened? They don't interact. The reason why? They repel each other. See what happened? They repel. But what if I go ahead and change this to north? See what happened? Well, of course, I have to explain this because I'm a science man. I had to get this from the transformer because I'm a precision person. The reason why I got this from the transformer, these are called laminate, and it's taken care of the eddy current anyway. And the holes are 100% right, because it's a precision job, it's done in a factory, laser precision. I couldn't do it like this. And then I have a copper wire inside. See, they are free to, you know, move. So now I have north and south. See what happened? When I bring it closer, see? See? Did you see what happened? They bunch up together. If I bring it a little bit closer, did you see what happened? So this is exactly what happened with north and south. So practically, even though if we cannot see them in space, but it's easy if you have an experiment like this, you can show people how they work. I have more over here, and it doesn't matter if I have like one here and one on the other side, it's going exactly half of it. See, if I have something like this, it's going to go 360 degrees. It doesn't matter. But one thing amazing about this flux lines, this is the best I could do. It's ugly, but you know, it explains everything. This is North Pole, and on the bottom is the South Pole. And the lines of forces are always perpendicular, so they have the right angle. Well, when they get to the edges, you see they tilt like this. If you remember a few minutes ago, I did it with the filing. You know, those little, you know, ferromagnetic, they tilted. When it gets over here, they're flat. But they get over here, they stick up. So of course this is not a good model, but it you know, yeah, it does explain that, you know, here is a sticking up because it's the pole, and here is less because it's not a pole. Like here, if I have 1000 Gauss, over here it'll be 300 Gauss. It doesn't mean it doesn't attract, it does attract. So you can see. Of course, this is another way. If you recall, I said if you have all those lines, they repel each other. See, this is exactly what happened. If I have two, you know, ball bearing balls over here, let me see. See, they don't stick together. The reason why, it doesn't mean this ball has north and the other one has a north also. They repel. No, no, no. It has to do with the flux line flowing inside because it's a ferromagnetic. And then I have to explain about the iron, because iron is an amazing element in our life. See what happened? Oops. They repel. It doesn't matter how you push it, always they repel each other. There's another one. I did it with two rollers. Let me show you. These are also ferromagnetic, and these are, see, it doesn't matter how you do it, they don't stick together. Always they repel each other. Let me see here. See? I hope you guys can see. See? They repel each other. So this Gauss meter saved my life. And I believe this experiment you have never seen in any book or any place like this. I said, Vahan, if the two poles are repelling each other, how could you tell? Let me bring this a little bit closer. You can see. How could you tell what is the magnetic field? What will happen if the two poles are, you know, pushing against each other, like, you know, two norths are doing like this? It's exactly like a spring. And then I came up with this idea. This is the only way you can, you know, have two magnets, you know, on top of each other. Well, of course, they're both north. So what it is, I show you. I said if I measure the magnetic field on this face, and then this is facing the other one, and then if I put my probe here, which is extremely sensitive in the center, because this is repulsion, it's not going to use a lot. It's not going to show a lot of magnetism. But let me show you why. I hope you can see this. It's showing 500 Gauss. Here, let me see how much it shows over here. 700 Gauss. But imagine, exactly when you put this probe in the center, see what happened. Did you see? 28 Gauss only. Can you believe that? It doesn't mean there is no magnetism, but they push each other. But there's another side of this story. If I reverse this, that is going to be double. I hope I can show you on this one. Let me see. I think I can show it on this one. If you pay attention here, this is extremely strong magnet. Let me see how much it is. It's 1,450. Let's see how about the south on this one is 1,450. If I put my probe in between, I'm going to get more than 3,000. Over there, how much we get? Only 100 Gauss. Did you see 3,730, 3,714 Gauss? It's unbelievable how it is. I wasn't satisfied with this. I said, yeah, because there is a gap, 1 millimeter, which is a lot in science. So, like I said, I came up with my own idea, and this is the magnet. I killed myself to have a hole on it, and finally, after a week, I did. I said, one, if you go at the center of the earth, the gravity is so intense, it will just demolish you. Imagine this magnet originally on a face has like 1,000, but it's showing 370. But see what happened when I put this in a hole. Did you see? 930. Did you see? Can you see that? 930. 932. So I proved my point that, you know what? All these flux lines are traveling and then ending at the center. Exactly at the center. But when I had these two magnets, their center is not their center. Their center is where those two magnets join together. And if you remember, instead of 1,500, it shows 3,000, because it shows that, you know, lines of flux are going 360 degrees, and the other one also goes 360. So they meet over there. So that's why I got the double. So now you do understand that what do we mean by flux lines? What do we mean by, you know, how they do that? And then I also discovered something else. Let me show you here, which is important phenomenon in science. Like this one, let me see. This one has 570 Gauss, and on this side, I have 1,000 Gauss. If I have an iron like this, well, of course, this is only 1 millimeter. If I have 3 millimeters, it's going to be a lot. If I have an iron like this, I put it on this, what will happen? It will enhance it. But nobody explained why. I mean, in physics books or anyway, and now I measured this. Let me show you. I hope I got the right one. See? It's enhancing at least 30%. Well, of course, this iron is not thick enough. I have to use a different one. I have to, oh, this is 3 millimeters. That is so powerful. This one has 1,190 Gauss. Well, when I put it in this iron, see what happened? The flux lines are going through the iron. At the same time, they're coming back at the center of the magnet. So what happened? This iron is enhancing. The reason why the flux lines are not flying everywhere, it's just trying to, you know, get everything. It's collecting every, you know, unwanted flux lines or whatever. Now let me measure here, see what happened. See, 1,400, can you believe? Almost like 30% was enhanced. So most of the time, if you see the electric motors, not 99, 100%, where those magnets are, they have thick iron. So that is the reason why iron is enhancing. It's just, you know, flowing the flux lines inside. The best example you can see is the transformer. You know, I remember I was a kid, I was trying with, you know, playing with transformers and so and so. But what happened, I asked my brother, he was a good electrician, he said, if you don't have those cores, the induction will be much less. And now I'm doing physical experiment. I've always, you know, explained to a student, if you don't have iron, the, you know, enhancement is going to be so bad. You can get induction with only coil, but that is the reason why you got the, you know, the laminate all around the transformer, and it's just collecting everyone, and it's just concentrating all the charges. Without those cores, you won't have any, you know, induction. But the induction is so good with those. Well, of course, here I have to use a little bit astronomy. You know, I don't want to waste your time, but this is a good information. You heard about the sun, our star, and then you know about the 4 hydrogen that fuse together. We got helium, and then we got the sunshine, and then we got the energy. That's why we are alive here, because that our energy, all the energies have come from sun. But you know, our sun is not going to do that. The huge stars, maybe 100 or 1,000,000 times bigger than our sun, they do, you know, nuclear fusion. But guess what? The last one they do is the iron, the heavy metal. And that iron is so bad. Why? Instead of giving back energy to the sun, is getting energy from the sun. Can you believe? And the poor sun, you know, I'm not talking about our stars and the other stars, they die because they collapse in their own gravity. That's the way the iron does. And imagine, iron is so important in our life, and that isotope 56 is amazing, has the highest energy per nucleon. I mean, without the iron, we cannot give hemoglobin in our you know, blood and so, you know, center of the earth. You know, nickel is not going to do the same thing, cobalt is not going to do the same thing. So imagine how important iron is, even though it's causing the star to die, but it's okay, because at the same time, after millions of years, another star is born. So it's just laws of thermodynamics continues. I have another amazing device. This is called a fluke meter. Let me show you. Let me turn this on. Always I buy the best brands. This is so versatile. This is so indispensable. How amazing this device is, God knows. You can have the clamp open. Oops, I'm sorry. You can have the clamp open or even clamp closed. You don't even have to touch any electricity. It measures the magnetic field. It measures everything, you know, current, amps, and so, because this is so amazing. You see, this part is like a primary of the transformer. So anytime you have something like this, let me show you, something like this. So the flux lines are traveling through this. You can see here, I'm getting 4 amps. Can you believe? It's not even half a turn, I'm getting 4 amps. If I go faster, I can get like 20 amps. But I have to explain what I mean by amps. So what happened here, this has flux lines, is flying or, you know, traveling from north to south continuously. So what I do, this jaw is cutting through the lines. So what happened, this computer is showing me that, you know, if you have a small rotation or a slow rotation, you get 1 amp. Faster, you get more and more and more. But I have to explain, what do we mean by 1 ampere? Charles Coulomb was amazing. I think he was before Andre Ampere. Both of them came up with this idea that 1 ampere is the moving charges past the point. So you have to have frame of reference. If you don't have frame of reference, you cannot say this is 1 amp or 2 amp. This is the way the science works. You have to have frame of reference. And then Charles Coulomb came up with fantastic idea, which still holds after so many years. It says 6.24 quintillion. We're talking about 18 zeros. 6.24 quintillion primary charges past the point, we get 1 amp. And he was right. And imagine here, I get a little bit, and I get like 2 amps or 1 amps. See, you can see there. There is no way I can measure the amp with the other way. But see, this fluke is helping me. I have to explain a little bit about the, you know, charges, because Niels Bohr was an amazing scientist. Imagine, when we're talking about this, nobody mentioned this is electrons. Whole our life is depend on electrons. We are exchanging electrons with this element, with the other, and then we get like ions, and then we got the voltage, we got the current, and so and so. But unfortunately, everything in our universe is invisible. This is the only way you can cut through the lines, and then you can find out exactly what happened. If you remember a few minutes ago, I said I found a book in LA. It was published in 1960s. He was, I think he's not alive yet. His name was Dr. Howard Garish. And then he published a book. God knows that was my best, book at that time. I remember I was so young. I was 26 years old. And I bought that book. I remember he said if 100 million charges, 100 million flux lines are cut with anything, especially it was talking about induction, you get exactly 1 volt. I made this, and then I showed that in my experiment. If you go to Vahan Davudyan, and you can see how young I was. At that time, this was in year 2000, Earth's electric field, you can watch that. Gravity, you can watch, and then you can see I did those experiments, and then I proved and substantiated that Mr. Howard Garish was right. And I have to explain a little bit about the electrons, and they're flying from the north to south. Well, what happened, you all are science lovers. Niels Bohr was one of the icons, one of the greatest in the history of mankind. I would even say he was much better than Albert Einstein. What he discovered for the electrons, he got the Nobel Prize and so, spin of electrons. And I never forget in my life, him and Ernest Rutherford was one of the greatest physicists in the history of mankind. He said it's like a planet. We got the sun, and then we got Pluto, we got the other things, like Mars and so. They go around, and then he compared the electrons to what? To solar system. And you know what? I'm following their footsteps. I always, in my theories, I compare something. So Niels Bohr said, yeah, this is what happened. The electrons are like a, solar system, and he was right. So, and this is my idea. He was right. And then they're flowing from here to here. Well, what happens? Sometimes we have attraction, sometimes we have repulsion. Well, why? 2 young physicists, they were not even physicists at the time. And you know what? Let me tell you the names. They came to the United States after they graduated, they got their bachelor. They became the best physicists in the history. One of them was John Uhlenbeck, and the other one was Sam Goodsmith. And they were fine students, very smart students. There were so many theories. Wolfgang Pauli came up with the exclusion, and then the other and the other. They were not even finished yet. This guy came up with groundbreaking, with the breakthrough in science. He said not only according to the Niels Bohr, the electrons going through the, like orbiting like the nucleus, but also they have their own spin. And can you believe that? We're talking about many years ago, Sam Goodsmith and John Uhlenbeck did, and I believe in that. If they have the same spin here, look, they attract each other. If they have the opposite, they repel each other. That's exactly right. We're talking about Sam Uhlenbeck, I think, was like almost like 100 years ago. And how did they come up with this, groundbreaking or, breakthrough in science? And they were right. Okay. I have this experiment. Not experiment, this is another analogy. If you guys remember, a few minutes ago, I had a poster. I said, I compared the light. This is a convex lens, by the way. Said the lights are exactly like lines of forces, are exactly like lights. See, the light is come through this lens, right there, and then we have a focal point over here, which is the north pole. If I another one back to back here, so it'll be south pole. And imagine, The lights are exactly the same thing. Of course, Sir Isaac Newton did it with a different way, and I love that idea also. But they are not as good as lens because you have to tilt those. But the lens you don't have to tilt. If you have back-to-back convex lens, and always the focus is here, focus is here. And this is amazing experiment. You're going to love this because, like I said, most scientists or physics lovers, they do it with, they do it with, plastic or, white cardboard and that thing. But I realized I have to go further. How did I do that? I had to use magnets. Well, what I did, I had to rotate the magnet. Why did I rotate? I said because the reason why flux lines are rotating is exactly, you can consider this like a nucleus, exactly the way I said for the planets, and the flux lines are rotating. But the flux lines is not rotating by itself. The energy behind it is the electron. They are traveling by the speed of light. But how could I prove that? I said if I have a magnet, I can remove this from the compass because the compass is not going to show me. You see, this is from the compass. One side is south, one side is north or positive or negative. If I rotate this, see what happened. Did you see? It's always perpendicular to the north and south. But if I go this way, of course, this is not a big magnet. I have to get a big magnet. I can show you. Yeah, this one is bigger. See, if I get this north, you see, 100%, see, perpendicular. But when it gets over here, see what happens. See. Did you see what happened? It's horizontal because this is not the pole. See, now here we got the south pole again. So I hope I can do this. It's very difficult. See, if I rotate it this way, it's going to be horizontal. See, it's not going to change. And now you can see why the slinky is like that. It's always vertical and then goes gradually to the other pole. So it's gradual, it's always rotating. But unfortunately, we have no idea. I mean, it depends on how powerful the magnet is. So what happened, the lines are going from here to center of the magnet and again to the center of the magnet. Well, when we have two magnets, 4 magnets back to back, it's exactly like, I'm connecting 6 1.5 volt batteries, so at the end I get 12 volts. This is exactly like that. So this is going to be their center. So there's going to be another one here, so it's going to be north, south, north, south, north, south. This is amazing experiment, and I bet you will love this. This is pure science. Let me put this aside. I said, what if I go ahead and do my own experiment and show the physics lovers what do I mean by north and south. See, what I did here, you can tell, I got 2 south and then I got south and north. These are exactly 3 inches, and then you can see that red line is the center. I said, what if I use my Gauss meter and put it in center? I don't have to do anything. It proves, it substantiates my idea that, that here the lines are adding up, and over here they're pushing, like I said, I show my fingers, they're pushing against each other. Let me get my Gauss meter, I can show you. Let me see, where is my Gauss meter? Oh, right there. Sometimes it turns off by itself. Okay, I'm going to put it on 0, so the precision will be 100%. So if I have my Gauss meter, see what happened. If I put it where there is a repulsion, I measured, God knows, maybe 100 times. It is showing only 10 Gauss. Let me see if I can show you. Well, it's showing less than 10, yeah, 8 or 10 Gauss. But see here, because they add up, it's going to show more. Let me see. See, this shows 125 Gauss. And then Another one was I had to use the induction. Let me put this aside. This is my coil, and I worked on this 3 days almost. There is more than 30,000, and you know, I have great patience. I never get tired. Never get tired, because you know, this is my passion. And you know how difficult it is to use this? Unbelievable. We're talking about like a hair. So if I connect this to, I hope I can show you. This meter is an amazing meter. It's also Fluke, made in Holland. I put it on voltage so you can see. If I connect this to these two wires, I can use the induction. Let me see. And it doesn't matter which one is the positive, which one is the negative, because you know it's going to be alternating current, and it doesn't matter. They keep changing anyway. So let me see. I can show you first, and then I can put it on this, guys. See, if I have my, let me see, where is the magnet? Yeah, I can use this magnet. So imagine if I go back and forth and back and forth, see what happened? I'm getting induction, almost 1 volt induction. So I said, what if I put, you know, I put this, coil back and forth where they repel each other, the induction is going to be 0.7. Let me see, 0.7. And then here the induction is going to be much less. So before I do this, I had to use this, let me see. I had to use this Fluke meter first. Let me get this out. I hope you can see that. See over here, I got almost like 0.7 amps. See, because this, motion or back and forth, and we have 2 poles here, it doesn't matter, even though they repel each other, but we get some induction. See what happened? I'm getting less induction. But if I put over here, they attract each other, I'm getting more induction. I hope I can get more than 4 amps here. We'll see, good luck. 3 amps, but you know, unfortunately, I can't stop it. So this was one way to show, and another way is to show it with my meter here. See, if I go here, see, I'm getting much less induction. But if I go over here, they add up. So let's see how much. See, here I'm getting more induction. Well, of course, it depends on how fast you go. So this was another way. So you can see the induction is always important, and Michael Faraday was an amazing person. He came up with the induction anyway. And then this was my idea. I said, what if I have a magnet like this, which one is causing torque? And then my guess was right. When I have it between these 2 south, let me see, let me show you. See, there is no torque at all. See, the reason why I've got those 2 lines, I just wanted to show you when I have north and south, there is a torque. Let me show you. I hope I can show you here. Did you see? It's turning, but I think it has to be. It's not powerful. It has to be horizontal. So when I rotate this, when I rotate this, see? Did you see what happened? It's coming back. But over here, when I rotate, it doesn't come back. The reason why north and south are causing torque. Well, of course, you can use this in many things, you know. I remember one time I was in Regis University. This was year 2000, and then let me see. I think I'm going to have to cut this. And then most of the students, they were having problem how the magnets are. And then I had to come up with this idea. See how easy it is to understand this concept. Let me show you. See, I had to do these magnets with great precision. See, like this one is like a donut shape, and you can see S. Half of it is S, and the other half is N. And N is also has another one on this side. And like this one is an electromagnet. And there's no exception, they're the same. See, electromagnet is the same. You can see inside, we have half of it S, half N. Here, see, we have N, half of it S. And you know what? It doesn't matter if the flow of electrons are from north to south or south to north, because this, you know, it doesn't make any difference. This was another one, donut shape, but it's not as thick as that one. So it's exactly the same thing. South, and then we got south over here as well. We got north and north. And this is like the one I showed you a few minutes ago. This is like this one. Well, of course, it's not as tall as this. So this is cylindrical. See, you can see S and then N. Well, these are the north and these are the south. What happened is exactly half of it is S, half of it is N. And then if you get two magnets, they fly always. They go toward the north. Let me show you what I mean by that. See? I'm not doing this. Magnet is doing, see? They always fly. They go toward the north, see? Because one half is south, one half is north. So this is the one you can do it at home if you have a doubt why they're flying like that. So I'm hoping that you guys can see that how easy it is to understand how the magnets are. Let me see, what else do I have here? I have this tool. I made this myself. Let me show you. And these are exactly the way the, flux lines are pushing against each other. So imagine this one, they add up. See, the line is not getting broken. Did you see that? The line is not getting broken. But if I have it the other way around, line is broken. They don't add up. See what happened? They don't add up. See? This is uncoiling, so is that one. That one is coiling, that one is uncoiling. I forgot to show you this. This is amazing. You know, like two north or south poles. See, it's exactly like this. Imagine over here, they get more like this, and then they repel each other. They repel each other, see? And then I'm going to have to give you a little bit history about the magnet. And these are my ideas. See, I got stars. Well, of course, I think I showed this in the theory of separation of the charges. So you got the eccentric washer, you got the spikes like this, you got rectangle, you got washer, you got solid, you know, like a square. And then if I put the filing over here, it's exactly what happened. Here we don't get anything, but around the washer you got, and it's according to my theory of separation of charges, always, you know, they travel to the end. But this is important. If you recall, I had to use this in my so many theories, and one of them was the theory of separation of charges, and the other one was superconductivity. And I love this to scientists, if you recall. This is called the scanning tunneling microscope. Let me show you. And these two, Mr. Gerd Binning, and then it was, his name was Heinrich Rohr. They got Nobel Prize, and they discovered the scanning tunneling microscope. And if you recall, I mentioned and emphasized, re-emphasized, the scanning tunneling microscope shows in 1 millimeter by 1 millimeter copper wire, the charge in it, they got 1 billion, you know, dipoles. That's exactly what happened. We have the dipoles. And then I talked about the Earth, why we have north and south. And unfortunately, most scientists didn't pay attention to me because I don't have PhD. And they were thinking, what university did you get your PhD? I said, I don't have PhD. I'm just, like Albert Einstein. Always I work at home. I did my own experiment. But this is an amazing story. I want you to know that, what do we mean by the neodymium or the other magnets. And guess what? One neodymium can last 700 years. But ordinary magnets like this, probably 200. If they have no interaction with anything, because I had a good habit, let me show you. See, you can see here 1998. Whenever I buy something, I put, see how bad it is? But guess what? At that time was 1,000, like 26 years ago. Still they have like 800, 900 because of, the interaction with the other things. So we moved in 1998 in Denver, not in Denver, Westminster, Colorado. So because I was the handyman at home, and then I had to install my own shelves. I bought real good shelves, metallic. And then I don't know why I bought 20 bar magnets like this from Home Depot. And then back and forth I counted because I'm so stingy. Always I just wanted to make sure everything is okay. I could not find one. So what happened? One magnet went behind my shelf. Because it was iron, it was stuck behind. And then I used that shelf so many times I could not even tell what was there. It took 11 years, and finally we sold the house, we moved. While I was disassembling that, and then I realized, hey, there's a magnet here. I said, wow, that is a good experiment for me. So I got that magnet, I checked it out. Instead of 1,000, they had only 300 gas. Guess what, in that 11 years, because it was stuck to the iron, it exchanged maybe quintillion, charges back and forth and back and forth. It got weaker and weaker and weaker. But you know what? There was a way I could replenish that. I didn't do it. Well, what I mean, if the magnets are not interacting with anything, especially with iron, they will stay the same because those flow of electrons are the same. And amazingly, like neodymium, they conduct electricity. But this one is a ceramic. It doesn't matter. They don't conduct electricity. Last but not least, as a token of appreciation, you guys emailed me that, you love my theories, and, I appreciate that. And this is a good feedback for me because in science, if there's no feedback, there's no oscillation. Always you need the feedback, and your criticism was, constructive. Of course, you didn't criticize. You said this is not focused and so and so. I always take action. Now, this is the first time I'm using my computer. It's a brand new computer. I had expensive camera, but unfortunately, once in a while it was acting and then I was not getting focused. But now I'm hoping this is going to be my brand new computer. Hopefully everything is fine, it's focused, and you guys will understand exactly. Well, of course, you can see how big the sides are. I can't help it, but it's a good device, and my computer, the lens is fixed. I cannot zoom or anything. And as a token of appreciation, if you have any, you can invite me to any college or university. I'll be happy, I'll be honored. I come to a university, I bring my own stuff. I pay for all the expenses. I can even bring some experiment to do for you guys, and I'm not going to charge you anything. But like I said, I'll be happy to do that. Why? Because this is my passion. I'm here to promote the science. I'm here to teach people unique experiment in sport, in science, and animals and everything else. So thank you for watching, and I hope you love this video. And like I said, all of them are unique, and make sure you take a note. And then if you have any questions, you can email me, and I'm always at your disposal. I'll never get tired. I'll be happy to answer your question. Even if I don't, it's not shame. I'm not genius. I can dig it out for you and send the email to you that this is the answer, but it's not going to be my answer. I had to check with so many physicists and say, yeah, John or Bob or whoever, this is the answer. And then I'm going to satisfy you. Thank you very much. And if you like it, you can subscribe. Otherwise, you can at least have a good memory of, these are unique experiments. Thanks a lot and have a good day.